Section 10.4 could be split basically into two sections. One section with the title Central Tendency and the other section with the title Variation. They're two related but different concepts that are going to be sort of composed in this section. The first thing we're going to talk about is the central tendency, and you have seen some of these before, probably all of them, but I definitely know you've seen the first one, mean. So the arithmetic mean, or the mean, we're going to just refer to it as mean, is one way of measuring how things are sort of averaged together. So usually when you use the word average, this is the one you mean, right? This is the one you're referring to. So you guys use means when you do what? Where do you see means used? Grades. Definitely see it with grades. And that's the prevalent use that you guys see all the time, right? Is the idea of using your grades to do this. And I can't think of any situation where grades are done in a different way. They're done with means, okay? It's not the only way, however, to measure how something is sort of centrally located, or how things are sort of bunching together. Another way of doing it is to do a median value. So what a median value is a median value is the middle value. For instance, if you were to line all of the grades on an exam, if we had an exam in the class, we're going to do one here in a minute, but if we had all the exam grades and I labeled them in order from smallest to largest, or the other way, but they had to be in order, the value that's occurring very center in the middle of it would be the median. It's the very middle value. It kind of marks for us the place where 50% of the people got above this value and 50% of the people got below that value. And often that is how I will think of whether or not the class did well or not well on an exam too. That is one of the measures of tendency that I look at. Another thing is sometimes that middle value is not a single value. So if you have an odd number of values, there's exactly one that's in the middle. But if you have an even number of values, then you sort of picked them off from each side and moved your way towards the middle. All of a sudden there's two numbers that are in the middle. So what you do in that case is you take both of them and you add them together and divide by 2. So you find the halfway point between them. Okay? So that's what you do for medians. The third one is something called mode. Mode is simply the number that occurs most frequently. Okay? So for example, let's say that I was wanting to talk about the grades. We'll keep using grades since it's a good example for us to talk about. And I wanted to say, how did the class do on this test on average? And I had, like 10 people get 87. And then I had, one person get a 92, and one person get a 64, and one person get a 32. Something like that. I don't know, whatever. Well, overall, they got 87s, right? I mean, because the majority of them all got the same value, and it's pretty much what the class did. All right? So that's called a mode. It's just the number that occurs most frequently. It's worth noting that you could have something that's bimodal, okay? Something that has more than one mode, or multimodal. So if something occurs 4 times and another number occurs 4 times, then both of those are considered the mode. We don't do anything to sort of add them together or anything like that, like we did with median. Okay, so we could have something being bimodal or multimodal. You could also have something that has no mode. That is, every value occurs the same number of times. Everything occurs once, or maybe everything occurs twice. But there simply isn't one that has more occurrences than another one. And that's usually how grades work out, right? It's really not all that common for 2 people to get exactly the same grade. It happens, but it's not all that common. So we end up with things that are often no modes when we look at grades. Excuse me. All right, so what we're going to do is we're going to take some values and just practice doing this, all right? And part of what I want to do when I show you this is what I would expect to see if I asked you to do this, because there's a wide kind of variety of things you might do or might not do depending on your level of comfort with what we're doing. So the first one we're going to find is the mean. So generally speaking, what do I do to find the mean? Add them up and divide by the total number, right? So either you can do one of two things. You either are going to show me that you're going to write all these numbers out, and divide by how many of them are there? 7. Or, at the very least, you need to show me what happens when you add those numbers on top together. Okay? So what happens, grab your calculator, if you add all of those values that are on top together? I don't actually have mine written down. What was it? 139? Okie dokie. 139? And what is 139 over 7? 8? All right. 19.8. So at the very least, you have to show me, of course, your answer, and then one of the two previous steps. I don't really care which one of them it is, but one of the two. Okay? What that does is that allows me to know that you at least know the process in case you simply hit something wrong in your calculator, right? You hit something wrong in the calculator and all of a sudden you have 169 on bottom. That would be a problem, right? But I would know you knew what the process was to do that, okay? All right, second one, median. Literally, you have to put them in order. I don't care if you go smallest to largest or largest to smallest. It doesn't matter. I'm going to go smallest to largest. What's the smallest number? And then? Okay, there are an odd number of these. We already counted and there's 7, right? So if you sort of imagine going outwards in and marking off the outer 2 and then the next outer 2 and the next outer 2, eventually you get to one number in the middle because there's an odd number of them. What number is in the middle on this display? 18, and in reality it's this particular 18, isn't it? Yeah. So we've got 18 as our median. The nice thing actually in doing this too is because you've put them in order, it's very easy now to see the mode. What is the mode?
18 and 22.
Yeah, there's 2 of them, 18 and 22. Okay, any question on that? All right, let me show you how we can use this kind of information in a little bit different context. Okay, so we've actually know that the mean of the test scores, we've got 20 test scores, and the mean is 75. And what we want to find out is we want to find out the sum of the test scores instead. Okay, that is, if we added all the points together on the front of the test, what would have been the total number of points that people got? Does everybody understand the question? Okay. Any idea about how you would go about solving this one? Good. And so I'm going to actually write just a little bit more, Hannah, before you did that. So what we actually have, one way that you guys think about it anyway, is the mean is the sum over the number of scores, or the number of values. In this case, it's scores. So we can use that, right, Hannah? That's what you were telling me. So the mean is 75. It equals the sum, which is what we don't know. I'll call it x, because that's what you called it. And then the number of scores, which is 20. So what would I do to find the sum? Cross the multiplier, multiply by 20, right? So what is 75 times 20? 1,500. So the sum of the points on the scores would be 1,500. Okay, let's take that idea one step further. I put this example in when I had a boy in the classroom. There's no boys in the classroom this time. All right, the mean weight of 7 linesmen on a team is 230 pounds, and I was told that I had my numbers way off. They were so inappropriate, so that's unfortunate, but it's okay. So the mean weight of 7 linesmen on a team is 230 pounds. The mean weight of the 4 backfield members, 190 pounds. What is the mean weight of the 11-person team? So let me tell you what you can't do. You can't add 230 plus 190 and divide by 2. Why?
That's not the average.
Okay, it's not the average. That's the average of the 2 values. What's wrong with that? Why isn't that the average of the team? Say, okay, you're taking the mean of the mean when you do that. That's right. What did you have, Morgan?
One of the groups has 7 and one of them has 11.
And that's the problem. If the 2 groups were the same size, we could actually do that, and it would work out okay. But one of the groups has 7 people in it, and the other group only has 4 people in it. That's why it doesn't work. It's because they're unequal sized groups. Okay. So what are we going to do instead? Yeah, we can do basically what I did on the last problem. We can find the total number of pounds of each of the two groups, and then we can add them together and then divide by 11, right? Because there's 11 people. All right, so let's take our 230 pounders first. So we have the mean, which is 230, equals our number of pounds. I'll call it X over, that was for 7 linesmen, right? All right, so what's my next step? Cross multiplier, multiply by 7. So what does that give me? 1610.
Yeah.
Okay, and this is a number of pounds. I'll go ahead and write pounds here just to keep our minds active about what it is we just found. So this was our 7 linesmen. Then we had 4 backfield members, and we can do the same thing. So we have our 190. I'm going to call it Y just because it's not the same number we're getting. It's actually a different quantity, so some other letter. And we have 4 of them at this weight. And so if we do the same thing, what do I get for Y? What is it? 760. Again, this is their number of pounds. So how do I find the average weight? 1610 plus 760 divided by 11. What does that give me? 216.5. Does that make sense? Okay. That is the end of the discussion, if you will, about central tendency. There's 3 types of central tendency, and that's how easy it is. There's mean, there's median, there's mode. Okay? Variation is next. Variation is more involved. There's lots of ways to find variation. The simplest one is to talk about the range. The range is simply the largest value minus the smallest value. So if we wanted the range of weights on the football team, we'd take the heaviest guy minus the lightest guy, and we'd subtract their weights. That's all we would do. That's what range is. Interquartile range is the difference between the lower quartile, called Q1, and the upper quartile, Q3. So let me describe what the quartiles are. So if we talked about the median, it's the middle value, right? Well, if we split from the beginning to the middle value in half, that halfway point over here, like the 25% mark, would be the lower quartile, Q1. And if we split the upper half of the values in half, that upper quartile is called Q3. Okay, that upper, like 75% mark. So sort of in your mind, you might have this picture that looks something like this. Let me get my line back. So the middle value right there is called the median. It's also called Q2. And if we split this in half, this is Q1. And if we split this in half, this is Q3. Now, that doesn't necessarily split the interval in half. It splits the values in half. So we may end up with a ton of values in a particular area, and so it looks lopsided. And we're going to draw some pictures so you'll see what I mean in a minute. But what it does is it splits the values into quarters, into 25% markers. Okay? So the lower quartile is the 25%, and the upper quartile is the 75%. We can use those pieces of information along with 2 more pieces of information to create what's called a box plot. Sometimes they're called box and whisker plots. If you've seen them before, that might sort of sound familiar too. You use the lower quartile, the median, and the upper quartile. And then you also use the upper extreme and the lower extreme. And the upper extreme and lower extreme are just the largest and smallest values. Okay, so it's like what we would have used if we found range. We found the highest value and we found the lowest value. So we're going to use that same data set that we did before, and we're going to use this idea with that data set. All right, so we put them in order once before. Let's list them in order on this slide. Okay, so we had 12, 17, 18, 18, 22, 22, oops, and 30. Did I get them all? Okay. So we already identified that this is my median, right? So we exclude the median now. If we're sort of thinking in terms of a picture, it is that mark. Okay, it is the location on the number line or whatever, and we're looking now at all the values below it. So the values below it, they're exactly another odd number of values below it, which makes it really nice. So what's the middle point of those values? 17. So this 17 is Q1. And what about the middle of the upper values? 22, this one is Q3. And then let's also identify what is my upper extreme? 30. And my lower extreme? Okay, so, I mean, like, obviously this is a very small set of data. But it works the same way no matter how many data points you have. The only possible difference is what happens if there's an even number of values. So let me show you what would have happened had I had one more value, and then I'm going to erase it because I need to finish the particular problem we're on. But let's say we had all these same values as before, and one more. Well, the first issue is going to be the median. What would the median of this data set be? It'd be 20, because it would be halfway in between 18 and 22. So this number would be the median. Now 20 is neither 18 nor 22, right? So it cuts them in half. Yes? Oh, like if it weren't even? Sure. Like if one of them said 18 and the other said 21? Yep, you just you'd add them together and divide by 2. So you could have a decimal. Absolutely could. All right, so if you were looking then for Q, so this is the median, it's Q2 or M for median. Now if you're looking for the median of the first set, you use all 4 data values because we exclude only the median, and the median was 20, which was not one of my values to begin with. So what would the median be for, and this actually is exactly your question, Shayna. What's the median for the first half of the data?
17.
It'd actually be 17 and a half. That's Q1. And then what would the median be for the second half of the data? 26. Okay? Does that make sense? So it has a little bit different feel to it, but you're doing the same stuff. And of course, if you had more values, you'd simply have to count more values in or out in order to count, to make sure you've got the value in the middle. Okay, I need to finish the box plot, though, for the one we were actually supposed to be working on. All right, so to do a box plot, what you're going to do is you're going to draw a number line to start with. The number line needs to include the lower extreme value as the first value. So in this case, it's 12. And our upper extreme value when we get there is going to be 30. But be careful because I really want all the values to be represented somehow beneath there. Now, 12 and 30 happen to be both even, so maybe you just mark every even value. That's okay. So 14, 16, 18, 20, 22, 24, 26, 28, 30. They should be roughly equal spacing. You start making things unequal spacing and it gives a picture that's not accurate for the representation you're looking at. We'll talk more about that in 10.5 next time. The next thing you do is you plot your median. My median is at 18, which is here, right? So that would be my 18 mark if I've counted by 2s. And the way that I plot my median is above the curve, above the line, I do a small vertical bar. And I do the same kind of vertical bar for Q1 and Q3. So Q1 is 17, so that's right here. And Q3 is 22, right here. So I've got a vertical bar, the same height. Right here. And what I do, those should all be the same height. They're not quite, but what I'm doing is I'm going to connect the tops and I'm going to connect the bottoms into a rectangle. This is the box for the box and whisker plot. Okay? What it does at a glance is it shows you the median, Q1, and Q3. It tells you 25% of the data values lie between 17 and 18. 25% lie between 18 and 22. All in one fell swoop, you can see that visually. And then what you do to finish the problem off is you actually use the middle of that diagram and you go out to each extreme value. And those are the whiskers. So those are my whiskers. So they go to the lower extreme of 12, they go to the upper extreme of 30. But this is a graph, and we've been working with graphs in 2 sections now. What do graphs need? Titles. What in the world is this a graph of? And yeah, so these are, we'll assume they're grades so that we can write something down because we were talking about it. These obviously wouldn't be grades out of 100, I hope not. But let's say for the sake of argument that we need a title down here. And I'll put an example title for what could happen. These could be the grades from a quiz or something like that. We weren't given context on this particular problem, but all the problems you're working with, I'm pretty sure they'll have context. So if they have context, they should have a title that reflects that. Okay, any questions on the box plot?
Yeah, people are like lines on the end of the line.
The lines on the end? It depends on the books that you use. I've had books, I'm not sure if your book does it or not, that put lines on the end.
I do feel like I've just seen
I have had books that put dots on the end. Whoops, not like that. Like this. And I've had books that do nothing on the ends. And I think your book does nothing on the ends. It doesn't matter to me. If you want to put dots or little small lines on the ends, that's okay.
Okay.
Yeah. All right. So one way of talking about how the values sort of are different than the mean, how far spread apart they are, is to talk about this idea of range and interquartile range. And that's what that last diagram showed us. 2 other ways of talking about them is to find mean absolute deviation, which we'll abbreviate MAD, and to find standard deviation. And usually that is designated with a Greek letter. Either the letter S or the Greek letter sigma, which looks like this. Okay? So that's for standard deviation. Now we've got a word right here that we'll talk about in a minute, but let me go back up to mean absolute deviation. Mean absolute deviation makes use of absolute values to find the distance that each data point is away from the mean, and you take all of the absolute differences and you average them. And we'll do one in a table format so you can see how that works. Mean absolute deviation is easier to calculate than the standard deviation. Standard deviation actually has a square root in it. It's a square root of something called variance. And the notation for variance is actually either s squared or sigma squared. I don't know why they don't use a different letter for it, but basically the relationship is that the standard deviation s is the square root of s squared, variance. And I've got sort of a listed out step-by-step process to find variance here, and then to find standard deviation. So you find the mean. You all know how to do that now, right? You've known that for a long time. Add things together, divide by the number of values. You find the mean. Second thing is to subtract the mean from each of the individual numbers you're working with. The third thing is to square each of those values, which turns everything into positives. I mean, it squares them too, but they all become positive numbers. The fourth thing is to add all those values together. And then the last thing is the next thing is to take the average, so we divide it by how many values you have. That actually gives you the variance. So if you stopped right here with steps 1 through 5, you'd have variance. The last step, by taking the square root, gives you standard deviation. And again, what this does is it tells you how far away you are from the mean. They're a way of measuring how far spread apart the data is, right? Because it's very different when I give an exam if the mean is 72, but I have a whole bunch of A's and a whole bunch of F's that all average to 72, than it is if I have a 72 and I have a whole bunch of B's and a whole bunch of D's to average to 72. There's something different about that information. And that's what standard deviation and mean absolute deviation tell us, is they tell us that kind of information. So we're going to find each of the values on this one, mean absolute deviation, and then we're going to find the standard deviation, and this shouldn't say variation, it should say variance. All right, so mean absolute deviation. In fact, in both of these, what we're going to do is we're going to create a table of values. Okay? You can do your table however you'd like. I tend to do my table in numerical order. So I'll put all the values in the table in order that we've been working with. So this is 12, 17, 18, 18, 20, 22, no, there's no 20, sorry. Get the right there. 22, 22, and then 30. Okay, so far so good? You're just putting them in the values. Now, both the steps on both problems involve me finding the mean. I have to know the mean in order to do this. Obviously, I need the mean for the mean absolute deviation. And the first step underneath standard deviation says find the mean. So, I need you guys to find the mean. We already did this before. What was the mean? Was it 19.8? Okay. Just so that you're aware, too, there's actually a notation for a mean. If you ever see this written down, X with a bar on top, that's standard notation for mean. The other notation for mean, the Greek letter, is the Greek letter mu. So if you've ever taken a statistics course or if you're working with a book that has statistics in it, they're likely to use these notations, just so you're aware of that. All right, so what we need in the next column here is to take each of our values, we'll call these values X, and to subtract from them the mean. And to be honest, we really want the absolute value of this, which means that we don't have to worry about the sign. That's kind of nice. So in your calculator, you can take each of the values and take, so 12 minus 19.8. What is that? 7.8. How about 17 minus 19.8? 2.8. 18 minus 19.8. 1.8, and I've got that there twice. How about 22 minus 19.8? And I've got another one there of that. And then I've got 30 minus 19.8. Okay, easy, easy, right? Subtraction, that's all it is. And then with the mean absolute deviation, what we do now is we add these together and we divide by 7. All right, so if we add these together, what do we get? What was it? 28.8. Okay, and then to find the mean absolute deviation, we take that 28.8 and we divide it by 7. So it is 28.8 divided by 7. 4.1. So the mean absolute deviation is 4.1. Yes.
How come, when you get 12 minus 19.8, why is it not negative 7?
Say it again for me, Ashley.
When we did 12 minus 19.8, how come it's not negative?
It would be negative, but do you see those absolute value? There's absolute value signs there at the top. Yeah, that's why. So we don't. I'm trying to move these over, and I'm not really succeeding. Look at that. Eventually, we will succeed. There we go. It's all scrunched in there now, isn't it? All right, so this is mean absolute deviation. Next, we're going to do variance and standard deviation. All right, so the table setup is very similar. We're going to have a table where we have all these same values, and we're going to have the same thing on top with the x minus x bar. All that's the same. So all the columns match so far. So just repeat all the same information we already have, okay? So that's the first step. Same thing. You do x minus x bar. Technically, we can work with the absolute value because we're going to square them here in a minute anyway, right? And when you square things, the sign goes away. So absolute values are just fine. So we can do 7.8, 2.8, 1.8, 1.8, 2.2, 2.2, and 10.2. We do not need to sum them, though, okay? That's not part of this particular step. Our second step is to take all of these values and square them. All All right, so we're going to square each of these values. So we're going to take 7.8 and square it. We're going to take 2.8 and square it all the way down. So what do you get when you do 7.8 squared?
60.84.
Did I write that right, Morgan?
Yes.
Okay. What is 2.8 squared?
7.84.
1.8 squared? Was it 3.4?
3.24.
2.4, and we've got two of those. How about 2.2 squared?
4.84.
And we've got two of those. And then the last one?
104.04.
Okay, did everybody get those same values? Perfect. All right, so this is the step 3, right? Square the differences, step 3. Step 4 says we're going to find the sum. So now's the step where we find the sum this time. So my sum is the sum of all these. So we're going to add up all of these squared values to find the sum. Did you get one, Beth? Does that look good? Have anyone else that finished that part? Great. 188.88. And then we're going to divide by the number of values, just like we did in the last one. The average here. And what we're actually finding when we do that is the s squared value. This is the variance value. So we're going to take this value, 188.88, and we're divide by 7. What does that give me? 26.98. Excellent. That is variance. What do I have to do if I want standard deviation? Take the square root. So if I take the square root of the 26.98 that I'm running off the screen, looks terrible, doesn't it? What's that value? 5.99? 5.19. You can. As long as we've got at least one decimal, we're probably pretty good. If the directions tell you to do something different, just make sure you use the number of decimals it gives you in the directions. Yeah. Yeah, so 5.19, 5.2, something like that. All right, the last part of this section deals with what are called normal curves. Have you guys heard of normal curves before? You ever heard of a bell curve? Have you ever heard somebody say something like grading on a curve? Okay, let me tell you what that really means, because you think it means something that's not mean. You think when somebody says grading on a curve that it means whoever got the highest grade gets bumped up to a 100. And then we add that number of points to every score. That's what you think it means, isn't it? Did you know that that's not what grading on a curve really is? What grading on a curve really means is it means finding the average, the mean, right, the mean value for all the grades, and that would be the center value. So then half of the class would get above that value in a grade and half of the class would get it below. So usually what you'll see happen when somebody really is grading on a curve, and you don't see it very often anymore, but it used to be more common, is that you would end up with, right here would be your, well, let me see here. Roughly, these would be your C's. So the bulk of the people taking the test or whatever would get a C. We'd split this apart over here. You'd have the same number of B's as you did D's, and you'd have virtually no A's or F's. That's legitimately what you would see if you were really grading on a curve. Okay? Yes? If you got a 100%, you'd still have the top value, right? But let's say, for instance, that the mean score was 80, and you got a 77, right? Well, if the mean was 80, you might actually end up with a D on the test if you're grading on a curve. If there's 3 scores that were tied for the top, they'd all be up there in that A range. So it might mean, for instance, that if you had 3 people who scored 100, and then you had 2 or 3 people that scored 92s, that those 92s end up getting Bs instead of A's. It does not pay attention to the numerical value. It pays attention to how many people get sort of stuck in one of these areas of the curve. So I just want you to be aware that we're not going to talk about grading on a curve any more than that, but that's what it really means when you talk about grading on a curve, okay? Don't go asking your professor to do that. It's probably not in your best interest, because what it usually means is that grades actually go down, not go up. So let me show you what grading, or what these curves actually do tell us, though. All right, so a normal distribution is a smooth bell-shaped curve, okay, just like we've got drawn here, and it shows things that are symmetric. See how nice and symmetric this looks? This value right here in the middle is the mean. And then what we actually have is the distance to either side of this. You go 1 standard deviation. Now we've just learned how to calculate standard deviations, didn't we? Because that whole chart thing, the very last problem we did, and we got the 5.2-ish value, right? So standard deviation means that if you go 1 of these standard deviations in either direction, and it really is a normal curve, that 68% of the values lie within 1 standard deviation of the mean. I'll show you a practical application in just a minute, so bear with me while I finish explaining the pieces of this. If you go 2 standard deviations in either direction, so out to here and here, you have 95% of all of the data values. Okay, so if we were thinking about this in terms of grades, that would be 95% of the people end up getting probably B's, C's, and D's. Okay? And then if we go out 1 more standard deviation, so we went out 3 standard deviations in each direction, we would have 99.8% of the data values. Virtually 100, right? Pretty much everybody. So we have pretty much all of the data values if we went all the way to the left and all the way to the right. 99.8% of the values. Okay, so far so good? Have you ever noticed on the back of the nutrition label on the back of products, I'm thinking chips, tortilla chips, it will tell you how many calories, carbs, sugar, protein, whatever, are in a certain amount of that product. So far so good? Often, as in with the case of chips, it will tell you the number of chips, and it will also tell you the weight of the chips. Right? It'll say 14 tortilla chips is 1 serving, and it'll also say 1 ounce of tortilla chips in 1 serving. Well, if you really weighed out 1 ounce, it may or may not actually be 14 chips. Right? The chips are not all exactly perfectly the same size. Somehow they've done an average. So on average, if Morgan weighed out 14 chips, and Kenzie weighed out 14 chips, and Kristen weighed out 14 chips, and Hannah, if we all weighed out 14 chips, on average, the weight would be 1 ounce. But each of your individual measurements might not be 1 ounce. Okay? 68% of them would be within 1 standard deviation of 1 ounce, and 95% of them would be within 2 standard deviations of 1 ounce, and virtually 100% would be within 3 standard deviations of 1 ounce. The same thing happens when you look at the box itself, like of cereal, and it tells you that it weighs 12 ounces. Well, if you really weigh that box of cereal, it may not weigh 12 ounces. It may weigh 12.3, or it may weigh 11.9. But on average, if you weighed all of them, they would weigh 12 ounces. Okay? So one of the issues with the normal distribution is you have to do it a bunch of times for it to be able to make sense. So this idea of grading on a normal curve would not make sense in a class of size 20. It's just completely irrelevant. But if you had a class of size 500, it might actually work, because there's a big enough group of people that it might actually fall into those categories the way you expect. All right, so let's take a look at a problem. We're going to assume a normal distribution where an average phone call in a certain town lasts 4 minutes with a standard deviation of 2 minutes and we're asked what percentage of the calls last a certain length of time. So when we're working these normal distribution problems, the key to doing all of them is going to be, you need to draw me a diagram. You need to draw that normal curve. So that's the first thing you're going to do, okay? So you're going to draw or attempt to draw a normal curve. And it will help you to have a vertical or horizontal line underneath them probably. The value in the middle is supposed to be the mean, and in this problem we're told that the mean is 4. Okay, now we're not drawing this for the purpose of doing a title and things. That's not the point. We're using the diagram to get some information, so we don't need to worry about accuracy and that kind of. We don't have to worry about like things being spaced equally. None of that is really very important. We're just using it as a reference. It tells us that the standard deviation is 2 minutes. That is, if I go up and down one standard deviation, I would go up and down 2 minutes on this problem. So I would go up to 6, and I would go down to 2. And that's one standard deviation in this problem. If I do this one more time, I go out to 2 standard deviations, which means I would go down to 0 and up to 8. And in theory, we would go up and down 2 more. Of course, on this one, it becomes a little bit weird because we get into negative numbers, and of course, that doesn't make sense in the context of this particular problem. So this is the basic sketch of what we've got going on. So you're going to draw the picture with the mean in it, and you're going to draw the standard deviations out at least as far as they make sense. Now, this says, what percentage of the calls lasted less than 2 minutes? So in terms of your picture, there's the 2-minute mark. And the less than 2 minutes is all of the values over here. Does that make sense? Okay, now think with me. We know some percentage values. They're all over here. 68, 95, 99.8. You got all these values. How can we use those values, along with the fact that this graph is symmetric, to find the shaded part? Yes, and in fact, I'm going to do it just a little differently. We're going to assume that we can have the negative number of phone calls so that we don't have to think about it quite so detailed. But in theory, what we would do is exactly what Angela's saying. First of all of the area this way, how much area of the graph is sort of designated in green? 50%, right? I've got half the graph. That is 50% of the values. How much of the values are right here? Not 25, at least not necessarily. 34. Why 34? It's half of 68. So if I went one standard deviation below to one standard deviation above, I'm at 68%. Well, I'm only going to the standard deviation below. So this piece right here is 34%. It was from the last diagram, 68% in the middle of the graph. Yep. 68% is in the middle of the graph, from one standard deviation above to one standard deviation below. Well, we're only going from the middle to half of that. So we get half of the 68 for 34. Does everybody see the picture? All right, so what am I going to do now with this 50 and this 34? Subtract. So the red region right here that I'm working on is 50 minus 34 for a total of 16%. 16% of the phone calls lasted less than 2 minutes. Now, if you did it as Angela suggested, you're going to get a slightly different answer. Her suggestion was to only go down to 2 standard deviations below the mean so that those negative numbers don't make any sense. If you did that, it'd be okay. I would accept that as an answer. It's just you're going to have done more work because you've been extra careful to observe the negative value weirdness of the problem. Let's try another one. IQs actually are normally distributed. Yes.
Those percentages are always like the 68%.
Yes.
Okay.
If it is a normal curve, these percentages always hold true.
Okay.
Now, what will change is the mean and the standard deviation, and that's context specific. So, yeah. All right, we've got a IQ test. A mean IQ score for the test is 100. Standard deviation of 15, and we're assuming that the scores have a normal curve. That's really important to know, too. Just like Morgan's question is, why do we know that the 68% business is working every time? Well, because it's a normal curve. We're told that it is a normal curve. If you're not told it's a normal curve, it may not have this kind of distribution whatsoever. So you have to have that piece of information for this to work.
Is it going to be a normal curve?
It will be on the one that I give you if I were to give you one, but I would also tell you that it would be. So if you were working a problem where it didn't tell you, like in real life or a real world problem, it wouldn't have to work out like this. Yeah. And that's why the idea of grading on a curve doesn't work very well, for instance, with a small number of students, is because there's no way in the world that I would think or should think that it would be a normal curve. All right, so we're going to draw our picture. And our mean is what? 100, right? Standard deviation is 15. So we need to go one standard deviation out, first of all, to what values? 85 and 115. Okay, let's do it again. One more standard deviation out. Where would that put us? 70 and 130. One more time. 55 and 145. Okay, so far so good? We don't have any negative values to account for, anything weirdness in this one, right? It's all positives. It's all good. So the first question is about having an IQ between 85 and 115. So if you go from 85 to 115, what percentage of the values lie there? 68%. That is one standard deviation out. But that is not exactly what the question asked. What did the question ask? How many? Not what percent. So I know that 68% of them, I mean that is the correct percentage. How do I find out how many that is? You do it in a proportion, or at least you could, right? So one way that we've done before is write that this is 68 over 100 equals, in our case we could do x over the 1500. Of course, there are other ways to change percents into those. That's fine. You could do that differently. But this is one way to do it. So you cross multiply and so forth. How or what value do you get from this? Okay, and is it a whole number?
Yep.
Okay. So like this?
Yes.
Excellent. So roughly 1,000, specifically 1,020 students' scores lie between 85 and 115. So far so good? Okay. How about between 70 and 130? %, you bet. Well, you can do the same thing, right, Carrie? Yep. We're just going to do 95 over 100 equals x over 1500. How many students does this end up being? 14, 24? 25. So 1,425 students. Yes, Ashley?
Can't you just do 1,500 times 7%? That might make it this
Yes.
way. Okay.
Yes,
So
that's
I don't
another way
have
to do
set
it.
up a proportion.
You don't have to set up a proportion, no. The reason I mentioned proportions is because that's something we've done recently, but you wouldn't have to do a proportion.
That's easy.
Yeah, yeah. It just depends on how you think about it. All right, the last one does not simply go out to the three standard deviations. It's not 99.8%. So let's think about this one. It says, how many have an IQ over 145? So in the picture, I'm looking at these values out here. I mean, they should be under the curve, and my shading didn't quite do that, but that's where I'm looking at. How do I find those values? There's two ways to do it. Let me say that first. Kenzie, what did you do?
I did like 100% minus 99.8 and then divided by 2.
Okay, so let's pause here and you explain. Why did you do 100 minus 99.8?
It's like all separate.
Okay, so when we subtract the 100 minus the 99.8, we're subtracting off this piece right here, right? Everything, we're subtracting off every value that's between 55 and 145. However, that gives me both tails of the graph. So if we divide by 2, we just get the tail that we want. Does everybody follow that? Okay, that's one way to do it. So what value did that give you for your percent? First, for your percent. 0.1? Okay. All right, did you do it differently, Hannah? Nope. Did anybody think of it differently? There's one more way to do it. The other way to do it is to have recognized that, excuse me, I don't know, sort of to have done it backwards. The 99.8 in the middle, right? And then divide that by 2. So what is 99.8 divided by 2?
49.9.
So you could just find that this piece right here is 49.9, and then do 50 minus 49.9. They're doing the exact same thing. I don't want it to seem mysterious. I just want you to recognize that you could be thinking about it as, oh, I want to talk about half the graph and do all the graphs, in terms of half the graph. Or I can think about the whole graph, and then I have to exclude one of the endpoints. Okay, so we get 0.01%. How many students is that? What did it work out to? 1.5, and that's sort of a problem, right? So one of the things you do want to be careful with is that you're, especially Ashley, if you're thinking about this one and you were just going to do it with percentages and not with proportions, is that 0.1 as a number is not 0.1. So you'd have 0.001. You guys remember that from when we were working with decimals back in chapter 7. And if you do the proportion or you do that percentage set up that way, you end up getting 1.5. And this is a number of students, so you have to round. And I really don't even care if you round up or round down. So I just say regular rounding rules would be appropriate, which means that this would be 2 students.
Where did you get 1.5?
But one way to get it is with a proportion. So if we do a proportion, we can set up 0.1 over 100 equals x over 1500, just like we did on the previous problems, and then cross multiply. And you'll get the 1.5. Okay? Any questions on that? All right. Last section of material is percentiles here. You have seen percentiles used, and you will continue to see percentiles used probably your whole life in one facet or another. Where have you seen percentiles used? Doctors. Sometimes they'll do, especially with young children, some of you guys will be moms, and they will give some kind of a growth chart, and they look at head circumference, height, and weight, and they'll say, you hear moms say, my kid's in the 90th percentile, like there's some sort of big achievement to that. So yes, there's some sort of an achievement to the fact that your kid is tall. Ooh, he had tall parents, go figure. All right, so we've got this going on, these kind of growth charts. Where else do you see percentiles used? Testing, and that's where you guys are going to see them if you stay in education, right? Testing. So when we use percentiles in testing, it's very interesting. I remember getting percentiles back when I was younger, and there's a very distinct difference between somebody saying they were in the 90th percentile and somebody saying they got 90% on a test. 90th percentile means 90% of the people who took the test were below you in their score. That's what it means. Okay? To get a 90 on the test actually tells you how well you did in reflection to the test as opposed to in reflection to the other people who took it. Percentiles put you in comparison to the other people who took the test. By that very nature, it means there have to be people who have lower percentiles, right? It means not everybody can do well on the test, or somehow it didn't make sense. Like the test itself did not measure something. That's weird, right? So in theory, you could get 95% correct on the test and still be in the 50th percentile. It just means that people got higher than 95 on the test. You did great on the test, but not as good as your neighbor. Okay, so percentiles are real tricky. You have to be really careful. They're not measuring you versus the test. They're measuring you versus other people. All right, so here's an example. Excuse me. Example number 9. Junior was ranked 50th in his graduating class of 325 students. Liz was in the 50th percentile of this same graduating class. Which student had the higher GPA when they graduated? There's a couple of ways to think about it. So what would you do if you were processing this information?
Split 325.
Okay, so we could take 325 and split it in half. Who is this going to relate to? Liz. So this is Liz. 325 divided by 2. What's 325 divided by 2? Okay, so this is 62.5. I'm sorry, thank you, 162.5. 162.5, which means that 162 people need to be below Liz, 162 people need to be above Liz. She is right in the middle. She's the 163rd person. So she is the 163rd person in the class. So if you put their GPAs in order from smallest to largest, she's the median, right? She's the one right in the dead center. She's the 163rd person in order. How does that relate to Junior? Yeah, it says he was ranked 50th. So he's above 163, right? Yeah. So Junior is ranked higher. Because he's the 50th person in order from highest GPA to lowest GPA. He'd be the 50th highest, right? 50th highest. We would always talk about the first person in class being the top grade, not the smallest, if you were thinking about that sort of maybe backwards. So he's the highest, so he has the 50th highest GPA, where she has the 163rd highest GPA. The other thing that you could do is you could figure out what percentile he's in, right? So we sort of reverted to figuring out where they fell in the mix, right? Who was in order. We could actually do it the other direction too. We could say, oh, look, he's 50th out of 325. So if we do 50 out of 325, we could figure out what percentile he is and compare it to her 50th percentile. And we could get a value that way too. All right, one correction to make to your example, to your homework, number 11, mark it up. Okay, you don't need to do number 11.